Okay.
That's the biggest part I like the most, was agree to agree.
And what did that mean to you? What was that?
Just that, I mean, like Rochelle and I will have two different ways of getting to the same point.
Okay.
And then we'll agree we got the same path, the same destination, but our ideas went two different directions.
Okay. So did it just say that anything is fine? Did it just say that all paths are okay?
You have to double check, like especially with what was the first example. That's like the students thought they knew what it was when they came to group work, and then she's like, "All right, everyone write down your own response now." And 8 of the kids couldn't even do it in the first place because they all just said, "Oh yeah, that's right."
Okay.
So it's important to make sure everyone does understand.
Okay. So Graham and then Beck.
I really liked this presentation of the constructivism and how what students make sense is what they make sense of it themselves. So the outside influence isn't so important, but them building the ideas themselves. And then he wraps that into saying that it's like a framework, it's a background. I'm not saying that we should just give students problems to work on, but it should be built around building up the ideas for the students so that they really take in the information.
Yeah, so like as a teacher, you have an idea of what you want the students to understand, and so you present something a certain way with images, with words, with group work. And so, but then the image that they start forming of this idea may be something different, right? And that's yeah. So then what? So what's the conclusion, or what do we do?
Well, as instructors, you want to try to mold their idea of it to what you have in mind.
Okay.
And try to be on the same terms.
Yeah. So there's constantly you have to be checking, right? So it's like checking and having them. So by them communicating and them responding, and then we can kind of check to see. So, check.
I was just going to go off of what you were saying before, that like to make sure that the students are actually understanding, and then the lesson how they were saying that once they came to actually writing down the meaning, they didn't know, because it's more than just like, I think that students understand recognizing the patterns they were talking about, or like when we were doing the functions in here, we could all see the like given values and the changes if they're proportional, but then and we were all kind of nodding when like people were suggesting ideas, and we're like, oh, okay, we got it. And then if you asked us again, okay, explain it, and how we were all explaining the change in like a different way. So just making sure that it's more than just understanding the patterns, and that they're making sense of like the interpretations.
Cool. Good. Rochelle.
I'm just going to say it kind of goes back to like questioning. We've been talking about questioning a lot and how important that is. And this article just really supports that, where you have to really kind of make sure as a teacher that if your student is following some type of path, and if they're kind of meandering off of the path that you're wanting them to kind of stay close to, you can question them and try to connect their ideas back to something, or just as like an overseer, really try and make sure that you're that guiding force.
The like main part of questioning isn't just to ask them a question to get the answer, but to get them to like reflect. Yeah, they were saying on their reading is that like instead of asking yes or no questions, that students are actually reflecting and thinking.
Yeah. So questions aren't about the answer, but about the thinking or a thought process. Okay. We'll go with Janae next.
When I was reading the article, I didn't really understand until I saw the examples. And then once I realized that it related to our last class, like now I know why you're constantly asking us questions and making us really explain. And sometimes it's confusing, and I try to, we try to figure out our words, and then maybe we do know, but we're not saying it the right way, and maybe we understand other people and their perspectives, and then we can resonate with that too.
Excellent. Yeah. Good. Richard.
I like that he pretty much destroyed the whole constructivism idea and was talking about radical constructivism, which is where in normal constructivism students have to build meaning individually, but with his idea it was we have to also kind of teach our students to be able to communicate their ideas to others, and it goes back to the whole agreeing to agree thing, because they have to be able to make sense of other people's work and kind of put themselves into other people's shoes, because it comes back to being able to understand how to think, how others think, And even as teachers, we have to do that.
Okay. So yeah, so how is it that we're aware and really understand what other people are thinking?
Well,
I'm not asking that question, I'm just saying, but you can keep up.
well, he brought up a good point. Like, when we design our instruction, we can't just think about how we would think. We have to imagine these images of generic, made-up students, and we have to sit there and think about how all these different students would think, and we have to kind of figure out how we can address that in our instruction. Kind of like how we're gonna bring a discussion together with all their different ways of thinking.
Yeah, and I find that in my own teaching, I find that happens when I start teaching a course several times. Like, so after I've taught it twice or 3 or 4 times, then I see all these things. I become aware of these easy traps that students will fall into, and so I'll try to warn them. Like, for instance, just today in calculus, we're talking about estimating a rate curve with a constant rate step function, okay? And one thing that I discovered last semester was talking about whether you're using the right or the right step function or the left step function. Do it on the screen so you guys see the video. So, and I've figured this out after a couple semesters that this is a really common thing that students do. So you've got wow. Let's try that again. All right, so you've got some function like this, okay, and you're going to create the step function. So is this a right step function or a left step function? So what I'm doing is I'm kind of trying to recreate this blue curve with constant rates. Okay, so is this left or right? Is this a left or right step function?
Well, left and then right and left.
Left and then right and then left.
No, just left.
Or
Just left.
Yeah, it's left. Okay. Yeah.
Why? So I've come to realize students think this is a right step function. Why do they think it's a right step function? Bennett, what's that?
Well, because the lines are on the right of the graph.
The line, okay. So yeah, kind of, right? Like, think of it like flags. Which way are the flags flying? To the right, you see? And it took me a semester or 2 to figure out that this was what was confusing students about, is it the left or the right?
It's almost like a direction, like it's pointing to the right.
Right, it's, yeah. But by left, we mean the function value at the left end of the interval, right? Correct? Okay? So it took me a semester to realize, oh, it's like they're thinking of these as flags, and since the flags are flying to the right, they're calling this the right step function. Okay? So that's little things like that you know, anticipating your students' thinking. And so then now I can, like, now when I taught this the first time, I said this right at the beginning. Don't think of these as flags, you know, don't think of these as, because it points to the right, it's the right. And I could emphasize what it really was. Okay, where did we leave off? Jessica.
But I wanted to point out something that I really liked that Dr. Thompson said. And he said communication happens only through interpretation. And then he said something else about when 2 people like really do communicate, it's because they've come to the same, I guess, mutual interpretation, where whatever they're thinking actually works together and agrees with each other, even if it's not necessarily the same thing that they're thinking. Exactly.
Okay. Cool. Other comments? Yeah, Maria.
I was just going to say that it aligns very well with the last article as far as like having questioning the students and having them build on this concept. So you as a teacher continue to question them and make sure they're on the right path. And I feel like that had to do a lot with the last article we read as well, is
concept through their connections or their understanding. I saw a lot of that in this one too, with the whole didactic object and like giving them something to talk about.
So you're actually answering one of these questions here, aren't you?
Yeah.
See, problems play the same roles in Thompson and Smith-Stein's frameworks. So you're arguing that they do.
Yes.
What do the rest of you think? What do you think about this question? So in the previous two articles, the role of problems versus this article. Bennett, was that a hand?
Yeah, I sense that it also was playing like the same role was the thing to talk about, the critically challenging task.
Okay.
The thing that starts the path, and starts what your discussion about.
Okay. Nice. Other comments on this question? Michelle?
I thought they were really similar, but I think that Thompson, sorry, I'm losing my voice, it sounds so bad. I think that Thompson kind of goes on and says that you can use a didactic object not necessarily like at the beginning of a problem or not necessarily like to end a problem. It can be just something to enhance an idea overall with or without like a problem to begin it. Whereas in Smith and Stein's, it almost feels like you almost need something like a problem or like a bigger question, and then you can dive into their method or like that framework. Where Thompson's is more like, you know, you can have almost anything that you really want to just fully discuss and really dive into with or without that problem.
Okay. Other comments on that question? Okay, so what is a didactic object? Daniel.
To put it in his words, something to talk about.
Something to talk about. Okay, so can we expand on that?
Well, like, I guess to do the third bullet point.
Okay.
The way you brought it up was you can break it into as constant rate of change in different ways a didactic object, because it's good that we were able to create it, but you would ask us more questions to see if we really comprehended what it meant. You're asking us, does that imply that y is proportional or has a constant rate of change to x? And I think it was Matt that said no, because it doesn't. That's not necessarily true. But what we do know is that the change in y is constant rate to change in x.
Okay. Cool. So so talking about that third question, what were the different? So how many didactic objects were there in that was it the painters? Was that the one we're talking about?
Yeah.
Yeah. So the painters problem. What's that?
A lot.
A lot, right?
Well, I mean, in a way, I kind of wrote about my reflections. It's one object, but as our conversation increased, it evolved with our conversation, where it transformed into something else that pushed the conversation farther.
Okay.
And it kept going with us. So in a way, it was one object that just changed.
When you say it, are you talking about the
painter,
the visual?
Yeah.
Okay.
Yeah, it kind of changed with the conversation.
Okay. So what? So you're saying there was one didactic object that evolved.
Yeah.
Yeah. Okay. Anyone? Is that the way you saw it? Anyone see it as many different didactic objects?
Yeah, there's a lot.
All right. So what were some of the? So if there were more than one, what were some of them? What?
Proportionality was one. Proportionality between the changes of x and y, the
Okay.
painter one, painter two, constant rate of change. It was all building to what we really wanted to see as a function, and what the slope that we wanted to see overall from painter one to painter two. So there was many, I think. They all built on each other.
Yeah, Richard.
I said the graph was one. Like, I was thinking of didactic objects was, I kind of thought of it as kind of the materials we use to, like the visual with the painters, that was one. Just the graph of watching their rates, just to kind of show us this relationship, that was also one. And then we connected it to kind of a chart of values of their proportions and the proportions of their changes.
Yeah, Grant.
I interpreted it as multiple didactic objects within didactic model, like Thompson mentioned at the end.
Okay.
You have multiple in one, and you're guiding us along a path using different objects.
Okay.
Within your framework.
So the first one was like the horizontal bars, right? And then what do we do? Then I wrote up in the what did I make up in the? then we made two tables, right? So each one of these is an object, right? So there's the object of the bars and how they change together. And then there was the tables. And then where do we go from there? What's after that?
I said that the diagonal lines that you
Uh-huh.
put on the bars later on as we were talking about the tables, kind of getting us to think about these tables, I thought that was like a didactic
Sure.
object that led us into more conversation.
Okay. Right, and then we made the actual graph, the actual Cartesian graph, where we put painter 2 on the y-axis and painter 1 on the x-axis, or the amounts they painted. And let's see what else from there. So then there was the actual graph, but then there was I drew triangles, right? So then I showed some corresponding changes, right? So all those things were something that I intended to have a conversation about, right? And to advance, this big idea. So Grant brought up the didactic model. What is the difference between a didactic object and a didactic model? Let's have this table here. Do you remember what it was? Anna or Kyle or Kyle number 2. What's the difference between a didactic object and a didactic model? Don't remember?
I can take a guess at it.
Okay,
to be
we'll take a
honest.
guess and
I didn't think it wasn't for me very clear, but from what I could tell between the first 2 examples and the third, which I think was more model based, I feel like he had more activities that went with the lesson because he had the kids like trace the rabbit like with their fingers and things like that. So I wonder if a model is more, I guess, interactive with the students than the actual object.
Okay, Julia, what do you think? Do you remember?
No,
Agree with that?
I don't remember him saying a didactic model.
That was at the end. That was in the last couple pages.
If I understood it right, I think the didactic model was like the blueprint or like the plan of like what he wanted to be talking about and what the path he really wanted his kids to follow along, and then a didactic object would be the things along that path that were going to get them to that main idea.
So the model, is it for students?
No, it's for the instructors.
Yeah, so the model is for the instructor. It's the instructor's set of ideas and interpretations and meanings, the whole picture of what they want to get across. And so then objects become part of that to that goal, to that end.
Yeah, so it's like a really certain case of like a lesson plan almost. You could probably think of it as like a lesson plan idea.
Okay? Is it a lesson plan, a didactic
It's
model?
more like a
I think you
framework.
could think of it as a lesson plan idea. I don't think it is, but like you could not use lesson plans and you could use didactic model as opposed to using the lesson plan.
Yeah, and in fact, that's interesting you say that because the way I think about my teaching is I definitely think about it more that way rather than I do try to write out sometimes a progression of what I'm going to do in a class, but my thinking is more about like what's the point of the class and
where
what.
do you want your kids to be at the end, whereas
Right.
a lesson plan is like what's your objective. I think that's different, different feel to it.
Okay, cool. Any more comments? Last chance.
Okay. I'm just gonna say Thompson has a very high vernacular because that first page, I was looking up the definitions of like every 5th word.
Did it get better after that though?
Yeah.
Yeah. So yeah, he is a true academic, but at the same time, he is about student learning. That's what's great about him. It's not just all up in the clouds. I mean, there's a lot of really lofty, hard ideas. He's teaching a class right now on Piaget. So Piaget is kind of the background of this article, right? In terms of constructing meaning, and that different people will construct a different meaning around the same object, right? So it's a whole class on Piaget, and so they're doing
masters.
Does he
yeah,
teach graduate level
yeah,
things,
that's a
or-
graduate level class.
Okay. Does he ever do like outside conferences or things? Where's he from?
Oh yeah, so
Undergrad?
his work in the U.S. when he goes and presents, it's not as well received. And why do you think that is?
Because it's an extensive math.
What's that?
It's away from the drill and practice.
Right. So if those who've read The Teaching Gap, our culture in math is what learning definitions and practicing procedures, right? So he's just not very well received in the U.S. It's kind of like the reaction is why do you make it so complicated? Why is it so difficult? Why just make it easy? Well, I mean, it makes it easy for the next 20 minutes, right? So this kind of follow the rules type of approach, or here's how you get to the answer, right? So that makes it easy in the next 20 minutes of the student's life. But what about in the long run, right? It's just not serving the student. And so that's kind of the reaction that he gets. When he goes to other countries where they have their culture, math education is more about ideas and embracing the problem solving. So Middle East, Asia, and they just love him. I mean, he's just So yeah, he travels the world, and he's, like I said, we're very fortunate to have him. So if you stay and do further work, you want to be in his class or somehow rub shoulders with him, because he's truly excellent.
I was just going to ask, as a professor, do you see it changing, or do you see it just staying the same, with no change, more the traditional way?
I see both. Because I'm in an environment where there's lots of people that we're going for it, right? We're trying to make a change, and so this Pathways curriculum is like one big example of it, and it's getting into the high schools, and lots of the high schools are embracing it. Some aren't. Some it's put in their hands. They're not really given. Well, they're trying to train everyone they can, but there's attitudes that are so deeply ingrained that when you get this curriculum, and if you don't believe in it, then your attitude's going to win, and you're never going to embrace it.
It's going to be a transition that's going to take a few years, because we're all being taught in Common Core, and we're being taught to teach our students like this, and we try it, and then usually our mentor teachers shoot it down because they're like, no, we have to teach the calculational method, but we keep trying,
right?
And probably when we become teachers, we're going to teach that way,
right? Yeah, so it's both. I think there's both. So we're just, what can you do? You have a sphere of influence. You do your very best in your sphere of influence, right? And then hopefully that makes a difference for some students.
Yeah.
But it's like turning the Titanic around,
Yeah.
Right? It's just not going to be an instant, easy thing.
Well, because as a future teacher, it scares me that, I'm going to be shut down with these conceptual lesson plans. And I would love to have that and have that foundation started, but it's like I may have to do one every week if I can fit that in,
right.
Because they do take time and they take extra effort.
So if you can find a school with other teachers who are like-minded and principal who is supportive, then you'll be able to make the biggest influence. But if all the math teachers around you in your school have a calculational orientation, and you're kind of this, alone in this ocean of a different, of the more traditional teaching, that's going to be a lot harder. So if you can find a school with other teachers supporting that conceptual orientation, especially in a principal who supports it, then you'll find you can have a lot more impact.
Yeah, I've had 2 internships now in a row where one person will write the geometry test for all the geometry classes. I mean, if that teacher isn't thinking pathways, there's no way to fit in your test because everyone's taking the same test.
Yeah. Good discussion. Any other comments about your current experiences in high schools? Yeah, Daniel.
Well, in our other class, we were learning that we have cycles. Sometimes in the 50s, they'll have we want more, scholarly way of teaching. Then we go back to what we have in pathways, and we go back. It's like this giant cycle. Do you think the cycle is going to continue, or are we finally going to have a curriculum that's based only on pathways in high school at least?
Well, it's such a big pond. In some places in the pond, there may be lots of traction, and there may be lots of change. Whereas, maybe in another state or in another city, it doesn't take. So it's not such a all or nothing kind of thing, right? The United States has hundreds and thousands of communities, right? And so, in some local areas, in some communities, you may make some real progress.
Yeah.
And in other places you may not. So it's not kind of one or the other.
Yeah.
Does that make sense?
Yeah.
I was going to say, teach conceptually of a lot of things. I think that from my internship, what I see is there's a lot of opportunity, in the space of questions and the coursework to teach conceptually this composition notebooks where they have to like reflect and write, which I think is like interesting. She was really big on trying to incorporate like reading and writing in math too, and they had to like relate it like the functions to like a real life, like when they see that in real life, and like that's starting to get them to understand the meaning behind it. But I think it's just such a slow change because like Maria was saying, like teachers, it's scary to think of changing how when we learn how to do a calculational method.
Other comments? Anything to add?
How was your high school experience? Did you learn more computational or conceptually?
I would say it was more calculational orientation. I guess for me personally, I think where I ended up here was because I needed it to make sense to me. Like I wouldn't just settle for this is how you do it. Like, and I think I found that more out when I actually went and got my master's in math. Like I absolutely had to, in these classes, things had to make sense to me for it to stick and me to construct something meaningful that, you know, it was real learning. So I think I probably in graduate school is when I kind of realized my own internal kind of conceptual need, right? Does that make sense? But in high school, yeah, my calculus course senior year in high school, I would say was probably pretty calculational. At the same time, I loved it, like, you know, because it was when I was in calculus in high school that I thought, wow, it would be really cool to be a calculus teacher. Like, I just thought that would be a really cool thing. Well, then I spent the next 8 years of my life pursuing engineering, and but I came back around to what my real desire was. So even though I was in a calculational setting, I still kind of needed the conceptual and still was learning in a conceptual way, I think, just because of my own, that's the way that I needed to do it.
So would you like look things up on your own or just ask more questions?
No,
Or
I really can't remember that well.
so I'm just
I remember the teacher writing these long proofs and like these big things on the boards, like, and then we would take all the notes, you know, furiously and get them all, you know, letter perfect, what his notes on the board. So in that sense, it was more about the rules and the answers, and
It kind of still is.
what's that?
It kind of still is that way.
Oh, sure, I know. Sure.
I'm just wondering how it is if you've been used to the calculational ways to adjust yourself so well that you can actually teach as a conceptual teacher. Because for me, the conceptual thing is so new that as a student, I'm still struggling with it, let alone as a teacher being able to. And I'd like to, but
No, that's that's an awesome observation. I mean, that's the thing is that you have to evolve yourself. You have to, in terms of learning mathematics, you have to be there first, because it's everything that all your beliefs and values are what you're going to pass on to your students, right? So yeah, I mean that's definitely the first thing is you got to believe in it yourself and learn mathematics yourself that way. And so that's I mean, hopefully this course is bridging both those things together. That's kind of the goal is that I'm trying to give you problems and situations that force you to think and force you to understand and make meanings of things. And then we also talk about then from the teaching role rather than the student role. So hopefully this course is a helpful step on your journey.
and the readings were helpful too, trying to think about how I could plan lessons around because we had the 5 strategies and all that. So it's been
Good.
helpful, but still feel like I have so much more.
Oh yeah, well the fact that you acknowledge that is fantastic. I mean, because it is, it's a journey, and listen to you guys talk about this constructivism kind of idea, and I'm just, as I'm listening, I'm thinking about my own teaching. I'm thinking, wow, I really am not aware of how my students are making meanings of the things I'm teaching them. I'm not a little bit, but I just figure I understand it this way, and if I do this and this and this, they're going to understand it that way. And if I really think about it, it's like, okay, no, I'm really not sure that that's really happening. So I'm still on this journey too. You know. Other comments, questions? So what about these little graphing calculator problems that I'm giving you? And so I want to hear your reactions, your responses. How are those going, and what's happening as you're trying to figure these things out? Yeah, Marie?
I would say they're definitely challenging, at least for me. I find myself going back to previous notes in class or what we did in the graphing calculator during class or, previous assignments. And even though everything is so attached, it's still playing around with it. It's still kind of like, figuring out yourself. Even though you've already had some prior knowledge, there's still this new task that you have to take on. So I know you've taught me, and I always want to attack it and just like get the right answer. But then you brought me back to you have to start small. You have to break it down and start where something makes sense and be able to construct something to where you could build on. And I think that's helped me a lot because they are challenging.
Okay, cool. Matt?
It was interesting. I was thinking about it last night. Is like I watched the YouTube video of like what the project was, and after I'm like, well, there's no like guidelines. There's no tips for the box problem.
The box, okay.
That's it. Like you just showed us the picture.
Right.
And I guess just I'm so used to. All right, here's the math problem. Here's the formula you have to follow. Here's the steps. Do it another 15 times and turn it in tomorrow.
Right.
Yeah.
And so my brain is so used to that after watching the video, I'm like, now what? And I just like really had to like stop and think like, all right, I need to break it down for myself. It's just weird trying to get out of that habit.
Yeah.
Okay. Richard?
Okay, so this is probably like, these assignments are usually like one of the few homework assignments I've ever actually looked forward to doing when I get home. Just because like, it's something where we get to combine our skills with math and make something, like actually produce something. And it doesn't have to necessarily be used to convey an idea, we get to actually make something, we get to see it live, I guess, because like we see something that we created and it's completely human.
Yeah.
And I just think that's interesting. And then we can always use this later on.
This is the beauty of graphing calculator, because it is just purely a mathematical, it just takes the mathematics and does what you tell it in terms of the mathematics. So it's such a great learning tool to give students assignments to develop something in graphing calculator, because it's all based on the math and it will just obey the math that you tell it, right? It just does that. And so if it's not creating something the way you wanted, then your something's wrong with your mathematics. Danielle?
Kind of going off of that and what she said, like, I really just find that breaking it down, like, task by task, like, I looked at the first line and I was like, okay, I'm going to focus on this one line, and it needs to do this on this end, and then I will, like, try a few different things, and then when I got that to work, I'd be like, okay, then this needs to happen over here, and then once I, like, finally figured out how, like, to get one line to work, it was so much easier to, like, build on that and finish the rest of the assignment and just sort of fill things in here and there.
Okay, so this is a key ability that you have to have. If you have a big, challenging project, can you figure out, can you see a sub-goal? Okay, can you make a sub-goal, a smaller task that seems attainable? And it's like, okay, if I can just figure out this much of it, I'll have something to springboard from, right? Or I'll have something to build upon. So this idea of, but so that's a skill, so coming up with the sub-goal or the sub-task is a skill in itself, right? So you have to be able to look at a whole project, and then you're looking at this box problem. So what is it that I can do, a smaller, easier thing that I think I can do that will lead me towards finishing the whole thing, or being able to complete the whole thing?
So, like, for the box problem, if you look at it, it's made up of a bunch of line segments.
Right.
So you have to figure out how to make a horizontal line segment and a vertical line segment, and how are you going to bound it based on the size of your cut. So
Good.
that's the sub.
Yeah. Maria?
I have a quick question. Now, is this graphing calculator, I don't know if you're the only one who teaches math at MTE 250, but is this part of the curriculum that you have to teach, or are you incorporating it with?
So this is the third time the course has been taught. The first time Dr. Thompson designed the course, and he taught it for the first time 2 years ago. And he designed it with, graphing calculator being, 80 to 90% of the course.
That's awesome.
Right.
Yeah, that's good. I was just wondering because it would suck if somebody took this course and was missing this whole
Right.
idea of graphic.
Well, taking that a step further, so this radical redesign of Calculus 1, it's absolutely required element in that course. So that course has been designed around Graphing Calculator and giving, so just like I'm giving you guys assignments in Graphing Calculator, they are also doing assignments in Graphing Calculator. Okay, so because we're basically building up towards the students themselves creating the mathematics that's going to be given a changing rate function, graphing the accumulation function, and that's half of calculus right there. So the students themselves are with my guidance, and as we go through the mathematics, they're going to be creating a graphing calculator file that does that.
I just have this problem with it where the help menu isn't very helpful because I know how to do a piecewise function on paper and I know how to graph it on paper.
Okay.
But when I tried to do one in here using that Control A, I couldn't figure out what format it would read because it just kept telling me I was doing
Okay,
it.
yeah. So when you have issues like that, you can email me, or we can sit down together and we can hammer those out. So yeah, there is some keystrokes and keyboard shortcuts and things like that that you have to learn, right? So
yeah, so I feel like that would be very beneficial to have like a manual for those kind of things that we could have, or even because the help menu. Have you looked at it? It's not that hard.
what's that?
The help menu mostly just teaches you stuff about math. It doesn't really. I mean, there is a page or some shortcuts, but it's not all of them. It's just unless
The
I'm
keyboard shortcuts doesn't give you all.
Well, I couldn't find how to use a piecewise function.
So that it's just Control A, but I guess there was in terms of the.
Yeah, I did Control A. I did.
So let's do that in a second. So let's talk more about that particular project for Monday. But let's talk about creating and accomplishing.
Actually, it's not that bad. The help. If you look on the entering formulas section, it tells you like everything.
What else? Okay, so all right. So what's something else about problem solving that you're finding is helpful? So sub goals is a huge one. So what helps you to get to accomplish these tasks that I'm giving you, Jessica or Jackie? Sorry.
Maybe like, well, it's kind of like different branches from it because it is like a sub goal, but maybe like when you're tweaking and trying to like say something happens, trying to understand like why it happened, like if it was wrong, like why did it graph that, like why did it happen that way, and then trying to understand what your mistake was and like modifying it.
That's excellent. As opposed to what? As opposed to what would not. Yeah. So just
like, I'll try to understand the meaning and I'm like, oh, I think that's what it is, and I'll type it in and it's like something way different. I'm like, okay, well apparently I wasn't getting it, so like why did this happen instead of like what I originally thought was
Yeah, it's because Graphing Calculator again will do exactly what you tell it to do. So if something isn't right, why? What is it that I told Graphing Calculator to do, and why did it turn out like that? So that's excellent. So what should we call that?
Comprehending mistakes or questioning mistakes.
Yeah, actually deliberately questioning mistakes. Yeah, excellent. Really good. So and by doing that over and over again, then your understanding grows. Your network of understanding grows surrounding that thing that you're trying to do, right? And so that will get you closer to doing it right.
I would say another thing that I do when I'm trying to solve these problems is I base my methods on what I know about the problem. Like with the box, like kind of we're talking about, I know how to design straight horizontal and straight vertical lines. So starting off with my prior knowledge and then just building off of that to modify to make sure that I
Okay, so maybe awareness of how prior knowledge applies. Yeah, because you come to this problem, so you do know life. Like this is Matt's experience. He's like, I don't know, what do I do now? Well, Matt has a whole construct of knowledge and understanding of things related to this box. So it's about recall. Like it's about like recovering those things and being able to apply them to a certain problem. Yeah. Okay. Other things. Yeah.
It kind of goes off of prior knowledge of just drawing connections of previous problems, not really just prior knowledge, but types of techniques I've already used
Okay.
in similar type of problems.
Well, I'll just throw that on here. So knowledge, prior knowledge, techniques. Is that, can I improve upon that at all? Is that, apply, yeah. I'm just going to do that. Cool. What else? What else helps to make forward progress? Yeah.
I like to draw pictures on paper and then just kind of analyze each part of it. If it has to do with like sliders, I'll draw multiple pictures and kind of just try to analyze how if you move your slider, what's going to happen to our animation.
I think something happens in your brain when you write. When you have something in your hand and you actually write, like you journal or you write out something that you're thinking, something different happens, right? It I don't know, activates certain things that might have not been firing before. So yeah, so get a pen in your hand, write things out. Let's go with Jackie.
Just like taking small steps, I think, in general sense, all these are techniques of like not getting too lost in like the complexity of the problem.
Okay.
And like taking, and it's not so much steps with problem solving, but just sometimes I think you spend so much time on it that you get overwhelmed with it, and then you're thinking harder than you need to. So just making sure you remember to go back to these techniques and like take a break and then come back and say, okay, let me think of what my prior knowledge, let me question what was wrong, and then going back. So just taking like small steps.
Okay, and within that, I heard many sittings. Right? So what happens? I mean, you all experience this. You work on something, and then you go, you do laundry, you go to another class, you eat lunch, you go to sleep, and you look at it again later, and all of a sudden you have all these new ideas, right? So, yeah, so especially as the projects get bigger, you're going to have to give yourself more chance to have many sittings looking at the problem. I should say working on. Was there another hand?
Mine was just off of that. Just like I think better when I move around. So if there's a problem I'm stuck on, I'll just walk around. That's usually it helps me a
Oh,
lot.
cool. Nice. Okay. Anything else to add to this? Jessica.
I think persevering. Because that might be not the only person who's been lost and frustrated. So
Okay.
just
So there's an emotional component to this, right?
Yeah.
So we haven't talked about that yet. Certainly there's an emotional component. So how do you deal with that most effectively? So you said,
persevering.
okay.
So I guess not giving up in a way.
Okay, so perseverance,
Which I
not
did
giving
give
up.
once. So, but mostly I persevered. The hard problem.
Okay, others, hands.
I think to go with that is like really try and dive within yourself to figure out what is your question about the problem. If you can't answer it yourself, at least you have a question prepared as to like what is it that I don't understand.
Okay.
You just look at it and be like, oh, I only understand this little piece, but get at the heart of the problem and really ask, what is it that you don't understand, so you can go and research that part or look into that a little bit more, or ask someone a question about that specific topic and not just looking for the answer.
I think this idea right here is one of the biggest reasons students do not do well on exams. It's because they think they understand it, but they don't. So they come to a place where, they think they've got it, but there's all these deficiencies that they're not aware of. So becoming aware of your own deficiencies is huge, because then you can hone in on that and fill in the gaps where you need to, rather than just kind of floundering like, I don't get it. You know.
I think my problem is that I don't want to give up, so I need to get better at taking breaks.
Take breaks, yeah,
And learn.
because when you take a break, yeah, that helps. Anything else to share? Okay. So then I had so going off kind of a different direction, talking about these problems, is what makes a good mathematical solution versus what we call shape thinking. So what do you think I mean by shape thinking? What do you think? Have you heard that term before? What do you suppose, if it's versus good mathematical solutions, what do you think we mean by that, Bennett?
Well, I've never actually looked at shape, so I'm just guessing that's more like trying to shape the thinking of students. So it's like you see a problem like this, you do it this method, and this is the prescribed method to it. So it's like you're really telling them what to do, and they can't think outside the box. Then doing like prescribed like cookie cutter kind of like.
Yeah, so I haven't really given you any background at all, so that's not shape thinking. But yeah, good try, Daniel.
Does it have anything to do with what they said in the article about how students like look at the graph and they see it as like a piece of wire? They don't understand what they're actually looking at. They just see it in terms of like objects.
Here, so this is an example. What might students see if they're looking at this graph as shape thinking? What do they think?
The object moves parabolic.
What's that?
The object moves in parabolic.
Yeah, that was the flight of the ball, right? The ball went like this. Okay. So what could be really happening here?
You're going straight up.
It could be right, and so that would be the graph of height versus time, not height versus horizontal position, right? So they're thinking height versus horizontal position. You get this path of the ball, but this or whatever it is. So this thing could be shot straight up and then come straight down, and that would model its height-time relationship, right? So that's one example of shape thinking. So how does shape thinking apply to you solving these graphing calculator problems? How does that come into it? So that's a very specific example. So what would shape thinking look like as you're trying to solve?
Well, we've been doing a lot of shapes, so we've been just trying to mimic those best we could with equations we know.
All right.
In the recent box example, we might have used a lot of lines to make a box.
Okay.
Such like that.
All right. So what is the difference between a good mathematical solution? We are trying to reproduce a visual, right? We're trying to reproduce something that looks like, I'm giving you something, you try to reproduce what it looks like. So then we're good mathematical solution versus shape thinking, so the idea here is shape thinking is not good, right? Not good. So what's the difference? Daniel,
I was also going to say, like, when we're trying to reproduce the graphs, like, sometimes it's easy to get into, like, the guess and check mode, where you're, like, just going to keep putting things in until, like, get
Right.
in a circle. But you don't understand that, like, when something finally does work, like, why it works, why that certain specific equation is going to map that. And that would be, like, your
Guess and check. That's shape thinking. You're just going to put something in and look at the picture, and if it's not right, I'm going to try something else, and then look at the picture until it comes out. And you're not, right? Well, we said about this before. We're not questioning our mistakes to make meaning, right? So what else? That's good. That is definitely shape thinking. What else? Any other ideas? Yeah.
And then, like, it was obvious we had to use n because you used n.
Okay.
And just, like, kind of putting it in there and going, not really thinking of what is n besides that. I just have to use it.
Okay.
I'm going to move it around. Hopefully I get it right. I'm plugging it in.
Yeah.
But what is n? What is it going to do?
Exactly. Other ideas? Yeah, great.
It's like when you look at a graph, don't think of a line as just a line you're going to slap on there, but more of a function of points in a collection points that satisfy some.
Right, and regions too. Like, so these pictures, how did you see them? Did you see that sun as a locus of points? And so, and then your inequality is going to be all the points that satisfy that inequality. Is that the way you thought about it? Okay. That's the goal. So the goal is when you see a region or you see a graph, you see points. That's your image of it. Your image of it is many, many points. So that's the same with a region. So it's all points. It's gonna graph all points that satisfy the inequality that you put. You see? All right. So I'll just give you the kind of the rundown here. So yeah. So this is what you guys said. So good mathematical solution developed based on understanding and problem solving versus trial and error until the image looks right. That's what you guys said. Good. Next thing is, it's clear how it relates to the original. So if you, when I read one of your solutions as I'm grading your solutions, it's clear how it relates to the original question and givens. Shape thing would be no seeming connection without some kind of explanation. So I see symbols that seem random. I see command lines that seem random that don't seem to connect. So a good solution is doesn't require a lot of explanation because it inherently fits it's a piece of the puzzle towards the task at hand. Okay. Here's a big one that we didn't talk about. A good solution can be generalized to solve many similar problems easily. All right? Shape thinking, so it must be recreated every time if the inputs change. So if you want to do something slightly different, you've got to start over and do the whole thing over again, rather than just tweak maybe one or two things, and it will solve the new situation. Okay, so here's just an example. I want you to reflect on. Here's two ways to make the kite string. Remember this, the kite string from the ground up to the center of the kite. So just want you to have a conversation with the person or your table. Look at these two different ways to do it, and in the context of what we're talking about here. Go ahead.
Oh, okay. I did the first one, but I used positive T, and I ended up just restricting the P values. I think that's what I did. Trade my right.
Oh yeah.
If you make the T positive, I mean, because that's it served next year. So it was like you have 3 halves P. That's why I did 5.
Well, I'm just saying that if you wanted to change the string, you could have made the bottom one better. You could only have to change one or two numbers. Okay, but the top one, you can change
I like 2 hours.
Okay, So, what are your observations here about these two kite string command lines in light of our conversation? Victoria, what do you guys talk about?
We just talked about like which one like we did, which was mainly the top one.
Okay.
Like, you can think about doing it the bottom way.
So,
But the one on the top is more like almost like shape thinking, where you probably have to plug in points to regenerate a different line, whereas like the bottom one is more
what would you have to do in the bottom one?
what?
So,
Yeah.
Okay, sorry, go ahead.
What?
What would you need to do in the bottom one versus the top one if you wanted a new line segment?
To change the endpoints.
Yeah, so this one, just change the endpoints. That gives you a new segment, right? What about the top one? What do you have to do? You got to start over, right? You got to start over, find the equation, and plug it in. Any other observations about the two command lines? Okay, so there was another one I thought of, and it's the idea a good mathematical solution is the most efficient solution. Okay, so it accomplishes the task with the least steps and parts possible. As opposed to thinking about building something one kind of clump at a time. So it's like I got this and I got this, and then you just keep adding and adding and adding, and maybe something's wrong, so you put something over the top of it, right? And you keep going until it goes back until trial and error until the image looks right. And so what often happens with that is it's kind of haphazard, and there doesn't seem to be clear direction with it, and you end up with more than what you needed because there wasn't kind of an overall structure or goal to it, but it was kind of very piecemeal. All right, so let's call it the tumor approach. You just keep adding, right? There's just a new tumor every time. Okay. So it makes me think about, so how many command lines did it take you to those who got it done or almost done? How many command lines?
A lot.
Like, did you count?
I think between 15 and 20.
Okay, yeah. 15? Okay. Yeah, so that's, mine had 16. And then I was thinking about this idea of mathematical efficiency. How could you do it in less? Is there a mathematical way to create the open top box in less? And I thought about it, and I thought, I think I could do it in about 10 or 12. But so that's just, I don't, maybe that'll be a addendum to that little project down the road, maybe in a week or something. We'll say, all right, so can we do it in less? Can you cut it down to 10 or 12 or even 8 command lines? Okay. So, is that better? What do you think? Is it better? Is it better to be able to create that box animation in 10 lines versus 16? And if so, why? Is it better, Daniel?
Well, if you can simplify your solution down to the point where you're pulling like tools that we've learned instead of just doing like old-fashioned little linear equations, like a million of those.
Right.
Then it means that you're getting the concepts of using a graphing calculator and a plan.
If you can do it unless you understand something that someone who took more lines didn't understand, right? You obviously have understood and been able to do something that someone who took more command lines couldn't do. So yeah, what else?
You're able to draw connections between ideas. Just like, I know this line does this, this, and this, which is really similar to here. So I mean, being able to make those connections is a big thing.
Right. So these two command lines are so similar. Is there a way that can be generalized to do both things at once? Yeah. So it is better because it reflects maybe not in all cases, but it reflects a deeper understanding of what's going on. Other comments about that? So there was a question about the. So let's just start a new one and let's just make a piecewise function. So say y equals, and so Control A, and on the on PC it's Control Shift A. Is that right?
Yeah.
Okay, so what you're going to have first is you're going to have the rule for the first piece. So maybe it's, x squared minus 3x. Okay, and then to show the piece of that we're going to take, you're going to put if. If. Sorry, I did forget that.
I always said that I tried the comma and then
That's
just
how
like.
it doesn't work. Yeah, because it needs if, because it's gonna throw x's at this, and as it throws all the different x's at this equation, it's got to know which command line to go to. So if x is less than -1, it'll know to use this command line. Okay. So cosine x, if x is, actually, I'm gonna do one more thing. So I'm gonna actually make this a function. If x is, if -1 is less than or equal to, so less than or equal to is, on the Mac, is option, comma, or option, period. All right. Say less than, I don't know, 3. Okay, now watch this. So another thing you can do with these is we could say, I can say that when it's greater than 3, I can say the function is, say, e to the 1 over x. Oh, that's not what I meant. E to the 1 over x times, shoot, times f of x minus 8. Come on. Sorry. Doesn't want to go there. What the heck? There we go. If x, let's say 3 is less than x is less than 10. What's it going to do? So explained it. So it talked about. So what is this function going to do, especially if x is between 3 and 10? All right. Talk about what's going to happen there. Go ahead. Don't put it in and graph it. Don't look at it. So we're interpreting without doing it.
Okay, so we're gonna plug in. So if we just have a square and one square over there, we would set 0. After 0. We put them in cosine. That's just
Multiplication. Yes. That's multiplication. That's multiplication.
And you use that as a
Oh.
That's it.
The original.
it's gonna look at all.
Yeah, I was like listening.
It's gonna look at the values before.
Raymond, what do you think?
So I think it's gonna just grab.
No. Steven, what do you think?
Well, if it's x is less than -1, we grab the top one.
Right.
And then the same thing, -1 to 3, we grab the second one. But then for the bottom one, we actually have a function inside the function. So if it's at, so if you plug in 3, it'll be -5. So take the 1 over e to the 1 over 3 times by the top function, because x is less than that.
What will it put into that top function? -5. Okay, so yeah, so the principle, everything you said was right. But he picked x equals 3. What's going to happen? Yeah, so everything you said was right. But x equals 3 is this thing that's an undefined value here. So let's graph it and see what happens. Okay, what's going on here?
Looks like it's repeating it.
What about this right here? Some of you asked about this. What's happening there? So what is graphing calculator doing to that it's showing that?
Saying that maybe it can't, it'll never pass that. Is it like an asymptote or?
Okay, an asymptote. What do you think?
Oh, we don't know. We can't define when x is equal to 3. We only have when x is less than 3 when it's greater than 3.
So let's see if, I don't know if we can do this. Yeah, I didn't think so. Okay, so let's see if that, just this much, actually making it defined at 3 takes care of it. Nope. So is f of 3 defined?
Yeah.
We should be using the result x squared minus 3x with -5 substituted for x.
Oh, so it's just a really big value?
Yeah,
Is that what we're saying? Doesn't seem to do anything. All right, so this, actually, so I've opened up a can of worms here. We could talk about this for half an hour. But I just wanted to show you that this is what's called a recursive definition, because it's using its own function within the function. As long as the function value that you, the x value that you call upon is from a different line, it's fine. But if you end up calling an x value within the same line, it'll just get trapped in a loop and it won't be able to do it, right? So you need to, if you're gonna have a recursive function, then you need to be calling upon the function such that it would be invoking a different line of the function, and then it's fine. Okay, so that's a hint. What? What's that?
I thought it was because the input in F is always going to be
Yeah.
the 2 lines.
Yeah, it is.
So how come it's still
Well, yeah. So we need to talk about what's really happening here. But this is valid. Yes, this is valid. Yeah, that's valid. Okay, and then you have the. I think the average rate animator. That's self-explanatory. I gave you a video for that, right? There's there's a video for. So you have 2 mini projects due next Monday, and one is the piecewise generator, and then the average rate animator, which I showed you both on Monday. But then, if the instructions aren't enough, let me know. Okay, just if you have questions, don't hesitate to email me. And then we'll start. We'll start the next project is a bigger one. Okay. Thank you. No, we're no more critical pricing. We're done. Yeah.
I made some adjustments on my open text box now that we know how to use these.
Yeah, send it.
Can I send you
Yeah, sure.
I made mine where you